It does look like it.
Okay, great. Looks like we're recording now, so I can begin. Thank you very much for that introduction. I really appreciate it. It's great to be here. Thanks to everybody for attending. This is just my title slide with all my information that was just shared with you. So that's who I am, and let's get into this talk. If my slides will advance. There we go. Okay, so today I'm going to be talking about SETI, right? And so what we're going to do is we're going to go through brief history on what SETI is, how it's conducted, and then I'm going to go through some of the projects that I've been working on in SETI. So SETI. What is SETI? SETI is the search for extraterrestrial intelligence. And anytime you talk about the history of SETI, you've basically got to start in one place, and that is with the theory and the observation, which sort of happened concurrently. So a theory paper was put out by Cocconi and Morrison in 1959 that basically described what SETI is. So with the technology that we had at the time, as you know, as a human civilization, we understood what our transmission power was and our receiver power was. And based on that, knowing the distances to the stars and how light propagates through the universe, basically they calculated that if a civilization exactly like ours was on a very nearby star system, on a planet around in a nearby star system, their receiver capability would have the potential to detect our transmitters and vice versa. So they reasoned, okay, if there are nearby civilizations as advanced or more advanced than ours, and they're sending out radio signals directed at us, we should be able to detect them. We have the capability. So they put out the theory paper. Unbeknownst to them, at the very same time, Frank Drake, pictured here on the top right and the bottom left, had already worked this out for himself and started conducting observations in secret because he didn't want the rest of the scientific community to, you know, thumb their noses at him. But he began conducting these observations, knowing exactly what Cocconi and Morrison had just published. Even though he hadn't actually read their paper. So basically the theory and the observations were being conducted concurrently. So a lot of people tend to think of Frank Drake as really the father of SETI, the search for extraterrestrial intelligence. He's kind of the guy who basically kicked it off. And he did it in Greenbank, West Virginia. And you can see him pictured there in the top right as a young scientist at Greenbank, but then in the bottom left, that's actually him much older, standing in front of the tidal telescope that he used to observe the nearby stars with his Project Ozma, he called it. That is much different than the telescope that's pictured in the background here. The picture in the background, that telescope is the Greenbank telescope that we know of today. It's much bigger. It was built in the 90s. So, okay. So if we're talking about Frank Drake, it's really hard to get away from talking about Frank Drake and subsequently the Drake equation in basically any SETI talk that you ever come across. It's kind of foundational. Right after he conducted his observations, they put together a SETI conference, the very first SETI conference held at Greenbank with some notable scientists, Frank Drake, Carl Sagan, and a bunch of others that are notable in the field. And that's actually where they founded the Order of the Dolphin, which spawned the Order of the Octopus that I helped put together this past summer. Anyway, the Drake equation was famously presented by Frank Drake at this SETI conference, and basically it gives a rough heuristic idea of how many civilizations could we expect to find, right, based on the known parameters. And the caveat there is that you don't actually know a lot of these parameters. Since SETI was started, we have a much better idea of some of these terms, like the fraction of stars that have planetary systems and the number of planets that we think could be habitable around them. But we still have virtually no idea about the persistence of life in the universe or how long civilizations live. So this is a fun little, mental exercise, but it's not exactly a rigorous formula because the error bars are just impossibly large. So how do we conduct SETI search? Well, we have to start with the electromagnetic spectrum because that's where astronomy works, right? For the most part, all of astronomy works with just seeing the light coming from stars and analyzing that. And so in this image, you can see basically all the light that gets to the surface. And of course, the rainbow shows the optical light. Optical light penetrates to the surface just fine. That's how we see. But a lot of the other light in the electromagnetic spectrum doesn't penetrate to the ground. And that's actually good because the UV, X-ray, and gamma rays would kill us. So we're happy that the atmosphere blocks that out. But it doesn't tell us a lot about what those rays are doing if we just observe from the ground. So in order to observe a lot of this, we have to send observatories into space to get the full picture of all the electromagnetic spectrum coming in. But getting all of it all at once is unrealistic, and we can't actually really do that. We have to do it piecemeal. But we don't actually have to go to space for all of it. In some cases, some of it we can observe directly from the ground, like putting stuff on really tall mountains so that the light doesn't have to go through the entire atmosphere. But also in the radio, you notice that there's a big gap there. Radio waves penetrate through the atmosphere all the way to the ground, and it's really beneficial. And that's actually one of the main reasons why radio was first used to conduct SETI searches. And on top of that, there are a lot of other interesting features in the radio regime. And Cocconi and Morrison actually worked out that the efficiency basically of observing radio waves or observing the electromagnetic spectrum is better in radio than trying to do it in gamma, which is actually where they started because they were professors from Cornell who had an exciting new gamma ray lab in upstairs, and they ran the calculations and they're like, well, it's not going to quite work in gamma, so let's drop down to the radio, and hey, those calculations work. Anyway, so a lot of the early on theory behind SETI was basically just trying to figure out how do we do these searches? Where do we look? And why would we do that? So coming up with justifications. And basically it can be summed up by Schelling points, which is a term in game theory. So Schelling points, well, we'll get into what Schelling points are. So if everybody takes a look at this square that I just popped up on the screen here, right? We have 3 blue squares and 1 red square in a bigger square. And if I told everybody, we're going to play a game. We're all cooperating, but nobody can communicate with each other. Everybody has to pick one of these 4 squares. And if everybody guesses the right one, if everybody guesses the same square, we all win. But if anybody guesses the wrong square, we lose. How likely do you think it would be that we would all guess the same exact one? And the answer is, it's actually pretty likely, right? If we can't communicate with each other, but all we can do is pick one square and find out, did we all pick the same one? We're all going to pick the red one. We're all going to pick the red one, right? Because it's the obvious point. It's the thing that stands out. It's what's called a Schelling point. And there are natural Schelling points in the universe. Most famously, the 21 centimeter line, which Frank Drake actually used to make the very first observations, which fall in line right in the water hole that you see depicted in the top right picture here. You see the H line and the OH line. This 21 centimeter line is very famous in astronomy. It's a very natural feature in the universe, and something that we would expect other intelligent civilizations to sort of gravitate towards as something that is, it's known, super obvious to observe. And this is called the water hole because of the atmospheric effects. Water tends to absorb a lot of the electromagnetic spectrum. And so if you go too far to the right, you get a lot of water absorption and oxygen absorption. And if you go too far to the left, you get a lot of galactic noise. And so right in this sweet spot here, right in this lull, you get the water hole, where you get a lot of penetration, you get a lot of signal to the background noise. So things like the 21 centimeter line and an OH line would stand out here. So these are just natural Schelling points. So these are the sort of things that we sort of narrow in on, because we say, okay, other civilizations, if they're advanced enough to, send beacons out into space and try and communicate with us, then they have to know something about astronomy. And these are the kind of natural features that they might take advantage of. So that's basically where we started. Nowadays, we tend to use the axes of merit to facilitate our experimental reasoning. Sophia Sheikh, a recent PhD graduate from Penn State, who now works at UC Berkeley with Breakthrough Listen, came up with the technosignature axes of merit. And basically any scientist worth their salt in SETI nowadays has to mention this in their paper. And basically, it's a little complicated to go through all the things, but effectively it shows what it provides justification for doing any sort of experiment. You want to get your experimental idea aligned with the axes on the right here as much as possible, and that's not always easy or feasible to do, because a lot of times there's trade-offs, right? You move one slider to the right and another slider goes to the left. But the idea is that this basically helps justify like where we're looking and what the different types of experiments can teach us. So that's basically, so I made sort of a big leap here from where we started to where we are now, but this is basically where we are now. Modern radio SETI is conducted primarily by Breakthrough Listen. Of course, other institutions and researchers are doing this who are not necessarily affiliated with Breakthrough Listen, but when you talk about radio SETI, it's really hard not to talk about Breakthrough Listen, because they are the major player in the game right now. And the reason that they're the major player in the game right now is because they're heavily well-funded by a Russian billionaire called Yuri Milner, who started the Breakthrough Initiatives back in 2015 to get this going. And part of that is Breakthrough Listen. Of course, it's called Breakthrough Listen because it operates in the radio regime. But I want to make it very clear that despite popular images like you see in the movie Contact, nobody's actually listening to anything. We're not talking about sound waves here. We're talking about light. Radio is conducted in light waves. And so all our telescopes operate with light waves. So nobody's listening technically, but it's just sort of like an English nomenclature thing that we do. Anyway, so Breakthrough Listen is the major player in the game. They're heavily funded and they're observing all over the world. Their major observatories that they're using are the Greenbank telescope, where SETI got its very first start with Frank Drake, the big impressive telescope nowadays. And that's in West Virginia. They're also using the Parkes telescope in northwestern Australia, which is important because now they'll get so Greenbank is in the northern hemisphere in West Virginia, and Parkes is in the southern hemisphere, so they get southern hemisphere coverage as well. So now you have the entire sky covered by having telescopes observing on both sides of the world, which is excellent. And then they're also trying to get commensal observations going on the Meerkat telescope in South Africa and the Very Large Array in New Mexico. And you can see those observatories here in this picture. So what do we actually look for when we do these searches? We're looking for technosignatures. We're looking for signals that tell us, hey, this is a signal that is definitely artificial in nature. It can't be coming from a star or anything else. And one of the driving features is that it is narrowband. So we know of no physical natural process that can produce a signal, a radio signal, that is ultra narrow band. And that by narrow band, I just mean like really, really thin, like this thin yellow line you see here in these three panels. Feel free to ignore the red dashed line. That's just sort of trying to imitate the angle of these yellow dashed lines here. But what this is in this graph is a bona fide artificial extraterrestrial signal. This is what we're looking for. Unfortunately, it's ours. This is from the Voyager 1 space probe. And it's actually very useful because we know exactly what it should look like, and we can find it with ease. Voyager 1 was launched back in the 70s to do a number of things, but now it is currently just going out into interstellar space. It's about 150 astronomical units from here. An astronomical unit is the distance between the Earth and the sun. So it's 150 times that away from us. So it's very far out there and constantly sending back signals, telling us, what's going on in interstellar space. And so we can train our radio telescopes on that and see, are we able to detect things the way we think? And yeah, absolutely. This is exactly what we hope to see, and this is exactly what we do see. So what you see here, what you notice is that the line sort of skips every other panel, and that's because the way that we observe typically these sources is that you point at the source, and then you point away from the source, and then on, and then off, and then on and off, in an on and off nodding cadence, it's called. And the reason that we do this is so that when we look at the source and we see a signal, and then we look away and we don't see a signal, we know that that signal is only coming from that source, right? So if we do this nodding cadence and we see the signal in every single one, in every single panel, we know that that signal is not coming from that source. It's leaking into our detectors from probably the ground or GPS satellite or Starlink. Ugh. Anyway, so this is an exciting calibration, but it's not exactly a real detection. The most exciting detection so far, I say detection, but it's not really a detection, it's more of a candidate, and that's why it's called BLC1. This is the Breakthrough Listen Candidate 1. The very first candidate signal that got through all of the detection protocols that Breakthrough Listen set in place. So their algorithm was able to find a signal that appeared in all of the on pointings and none of the offs, and it elevated this signal to say, hey, maybe we have something here. There's a lot more that has to happen after that to, vet it and make sure that it's a legitimate signal. And unfortunately, it turns out that this is not a signal. This is radio frequency interference, or RFI. But it was a really exciting case because it's the first one that got through the preliminary round of checks. Also, the other reason why it's super exciting is because this signal was observed coming from Proxima Centauri b. Proxima Centauri is the nearest star system to the Earth. It's about 4.2 light years away. And so it's super close in astronomical terms. And it also boasts a planet, Proxima Centauri b, around the star that is a terrestrial planet, rocky in similar size to Earth, in that star's habitable zone. And so it's very exciting because there's a remote possibility that this could be a planet similar to Earth. Of course, could equally be similar to Venus or Mars. But anyway, the point is that this was exciting for a number of reasons, but it turns out that this is a false positive. Okay, so that is a very quick run through of where we started and where we are now with Radio SETI. I skipped over a lot in the middle, and I apologize for that. There's so much to talk about, but I really can't go into all of it. So what I want to do for you now is detail give you a bit of a whirlwind tour of some of the projects that I'm working on. I'm just going to talk about 3 here, starting with this one, although I'm working on a number of other projects as well. So we'll start with KIC 846-2852. I know that's a mouthful. And believe me, when I first got into astronomy, I was like, oh my God, all these stars with these numbers and letters, it's killing me. But you stare at them every day and you sort of get used to it. At least you stare at the same one every day and you're like, oh, okay, I know this guy. It's a lot of, there's just too many for all of them to have a name. But this one does have a name, a very special name, Boyajians Star. And in order to explain what's going on with Boyajians Star, I kind of have to take a step back and explain a little bit about exoplanets. So to date, we know a lot about exoplanets. We have detected and confirmed over 5,000 exoplanets, more than 4,000 with the transit method alone. The transit method is depicted in this picture in the top right here. So basically, you have a star that's emitting light at a certain brightness, and we can detect how bright that is. And then when a planet passes in front of it, the starlight will dim, just like when the moon passes in front of the sun, right? We get an eclipse and the brightness of the star dims. So we can measure that. We have to have really high sensitivity because these stars are really far away, but we can do it. And so we are doing this all the time, and we've detected thousands of exoplanets in this way so far, and it's awesome. So the graph that I'm showing here in the top right is what's known as a light curve. So the dip tells us basically how big the planet is in respect to its star. And so the first mission that we sent into space to do this was called Kepler, launched back in 2009, I believe. It was very exciting. And got us a lot of information. It stared at one patch of sky and found thousands of exoplanets around distant stars. And very soon after the Kepler was launched and people started analyzing the data, people immediately started to look for anomalies. We know what a planet passing in front of the star should look like. It looks like that top right curve. And for the most part, most of them look just like that. And it's cool, it's great, and there's different ways to look at it and analyze it. Some shapes are slightly different, but for the most part, they look exactly like that. So people were looking for anomalies, things that didn't quite make sense, and here's one that they found. This light curve was the one that was actually published by Tabitha Boyajian, the PI who first published this data, which is why it's named after her. And you can see that this is not regular. This does not look like that top right graph, right? The dips are irregular. They're oddly spaced. They dip and then dip again and then dip shallower. And it's very unusual. And honestly, nobody has any idea what's going on here. But when this was first discovered, people got very excited, especially people in the SETI community, because of something that was theorized a long time ago, actually very soon after Frank Drake started SETI in the mid-60s. A man by the name of Freeman Dyson proposed possible megastructures around stars. So if you assume that an alien civilization might advance in technology at the rate that we do and last for a lot longer than we do, maybe there's a very old civilization out there who has technology way beyond anything we can conceive of and might actually try to harness the entire power of their star. So they might try to construct a Dyson sphere. Dyson himself in a rebuttal paper noted that a sphere is unlikely to be the case. It would much more likely be a swarm. So you'd have like sort of orbiting platforms maybe. And it was actually recently shown with physics by my PI, Jason Wright, that it's the material properties of a sphere is unrealistic. So a swarm, maybe, okay, that might be physically possible. And so for a long time, people thought maybe that's happening. And so they set about looking for these things. And so far, nothing has turned up until this. And so the people in the SETI community said, could this be it? You know, if you have a swarm of things floating around a star, they might dim the star in very unpredictable ways. And so my PI, along with Tabitha Boyajian and the people at Breakthrough Listen, who had just started their campaign at the Greenbank Telescope, conducted some observations in early 2016 and late 2016 and early 2017 to see, okay, you know, maybe this is a megastructure, maybe there's an alien civilization there, maybe they're sending out a radio beacon as well. Who knows? Why not? It's an interesting target. It's a shelling point. So let's take a look. Unfortunately, soon after this, other observations were taken in other spectrums, in other regimes of the electromagnetic spectrum that basically implied it's super unlikely that these observations are caused by this, for reasons that it's not really important to go into. But so the idea of a megastructure is currently, and pretty soon after the claims were made, that it's disfavored. Science doesn't really think that Boyajians Star is likely to be the cause of a megastructure. However, the observations were already taken. So let's analyze the data, right? And that's been my job. So for the past year and a half, I've been analyzing the radio data that came from this star. And it has been difficult. And the reason that it's been difficult is because, like I said, this was pretty early on in the Breakthrough Listen campaign at Greenbank Telescope. So the process for taking observations wasn't really standardized. So a lot of the data is difficult to process. So I'm working through it, but unfortunately, I don't have any results to show you just yet. Right. So this picture just shows you what's the current favored theory is that maybe it's just a fleet of comets, or, well, they still don't really know. But other observations show that it's unlikely to be a megastructure. So I'm working through, right, like I said, I'm working through the analysis, but unfortunately I don't have any results to show from this project just yet, but I do have results to show from the next project, which we're going to get into now. And this is a project from the Astro 576 class that I took last fall, the graduate SETI course, which is where I learned all of this, well, most of it. And it's about, so last fall I took this class and we had to do a class project. And so we had to come up with the theory and do the observations and do the analysis. And I had hand in the observation and the analysis, not so much the theory, but it's pretty exciting. So the theory has to do with general relativity and gravitational lensing. I know that's a lot. I'll try to break it down for you, but you can see it's sort of depicted here what's going on in these three panels. When you have a massive object in space, it warps space-time, and light travels along space-time. And so, as you can see in the animated GIF here, light is traveling in a straight path, but it's traveling along space-time in a straight path, and if space-time is bent, then it will appear to bend around a massive object. So like a star or a cluster of galaxies, light will appear to bend. So light that starts out divergent from a source might encounter an object and then converge like a lens. You can see that in the other two images here. On the bottom left, this is an actual picture on the bottom left of a distant galaxy that is imaged around a galaxy in the foreground. So a galaxy in the distant background produces light that goes around a galaxy in the foreground and converges and focuses to our telescopes here on Earth. And so we can see the same galaxy on two sides of the other galaxy. So it's pretty exciting. The same can be done with a star. And so if you look in the top right here, light can pass around a star and focus on the Earth. And if those two rays converge in our telescope, it'll actually brighten. So you see on the middle panel in the right, that dot looks even bigger. It looks brighter, and that's because it's like a magnifying lens, right? That's basically what we're looking at here. We're using massive objects in space like a magnifying lens, and so we can use the sun like a magnifying lens too. However, the caveat there is that you have to be at the focal point, right? If you've ever held up a magnifying lens and just like held it right close to your eye, that doesn't really work, right? You have to be at a certain distance from the magnifying lens for it to work properly. And that's the case here. But the theory goes, if you get to that proper focal distance, perhaps, well, if you get to that proper focal distance, you can observe that focus signal, but it goes the other way too, right? You can also transmit through that lens and have it reach your target in a focused manner. And so you can both receive and transmit that way. And so the theory goes, perhaps instead of trying to communicate across the galaxy by just sending one signal straight line to whatever other distant star, perhaps an advanced civilization will have set up something much more like the internet, an interstellar network of relays that they use stars to focus their beams and shoot transmitted signals at other probes in other star systems, and just sort of relay the signal across the galaxy. Maybe that's why we're not really detecting anything, because they're all doing it this way. And so maybe that's happening, and they're using our sun to do so. So our theory wasn't just pulled out of thin air. This has been in the literature. This theory has been proposed before in the literature, and but we're actually the first ones to try and take observations of where we think these probes might exist in the distant reaches of our solar system. It's actually technically outside of our solar system. It would be at about 500 AU or more. And if you remember, Voyager 1 is at 150 AU. So 500 AU is really far out there. Technically in interstellar space, depending on how you define things. So anyway, the idea is, right, maybe there is an interstellar probe out there at the focal point, right, at what you can see in this Einstein ring in the bottom right picture here. Maybe there's one there, and they're using our sun to focus light rays and communicate with exoplanets around a distant star system. So in order to figure that out, right, we just say, okay, well, if they're communicating with Alpha Centauri over there, then the probe would have to be on the opposite side of the sun, and that's called the antipode. So we basically just trained our telescope at the antipode of Alpha Centauri and said, okay, if there is a probe trying to communicate with Alpha Centauri, it's got to be over here. So let's look. And that's what we did. We went down to, there we go. We went down to Greenbank Observatory in West Virginia just this past November to take these observations of the Alpha Centauri antipode, just to see if there's a probe out there who's communicating, using our sun to communicate with other star systems. And so these are all pictures that I took with my phone, or had somebody take of me with my phone. was a really awesome trip. I highly recommend if you ever get the chance to visit. It's in a radio quiet zone, so if you're attached to the hip to your phone, keep that in mind. but it was really great. You can see the telescope that we used in the top left there, and in the bottom right as well. That is the Greenbird telescope that is about 100 meters in diameter, which is about meters, about a yard. So it's like a football field wide. It's actually a little bit more than that, but yeah. And then so in the top middle picture here, that's the picture of the lab where we actually conducted the observations. It's all done remotely. Fiber optic cables run from the telescope to the lab, and you have to walk into a Faraday cage and do everything shielded, because all the electronics could easily give you RFI, radio frequency interference, just by being on. So anytime that you go anywhere near the telescope, they won't even let you bring your cell phones or anything. If you have anything electronic at all, even like a watch, they'll put it in a tiny Faraday cage on the bus, and make sure that there's no interference. Because this thing is huge, and it is super sensitive. It's really incredible what they can do. In fact, in the neighboring community, they even have a patrol that will go around, isolate any radio signals, and say, hey, you're going to have to turn that off because we told you that you can't live here if you have Wi-Fi. So don't. They can actually localize radio signals. It's that sensitive. They use a different thing for it, but anyway, I digress. And then the top right picture here is the Science Center. It's actually very impressive. So again, I recommend highly that you go if you can. The bottom middle picture here is me standing in front of the Drake equation plaque in the Frank Drake lounge in the dormitories where we stayed, and that's the place that the very first SETI conference was held with Frank Drake and Carl Sagan and a number of other notable scientists. It was really amazing to get to go there. So anyway. So we went down, we took some observations. Sorry for the digression, but it was really cool. And then it was basically up to me to run the analysis. So we took the three observations in 3 bands, L band, S band, and C band, at these frequency ranges. L band is where you get that water hole, that H1 line. And then I ran it with Turbo SETI, which is the algorithm that Breakthrough Listen uses to analyze the radio data and produce dynamical spectra, which we commonly just call waterfall plots. They look like the plots you saw before. However, you'll notice this one looks a little different. This is the most promising result that we have from our observations. It occurs at the drift rate that we expect. Don't worry about what that means. It's not very important, but it's an indicator that is exactly the frequency that we're looking for. Again, ignore the dashed red line. The computer thinks it's smarter than it is sometimes, but we do know that it is working. We test it all the time. But again, you'll notice that this is not, right? This doesn't look like what we observed before. So, inquiring minds want to know, how is this a detection? Well, if you zoom out, this is the signal that they actually see. And so this makes it much more clear that this is just RFI, right? You can see the same signal propagating in the on, off, on, off, on, off, on, off cadence. It's complicated because humans are very clever at doing very complicated things with technological signals, but this is what it is. So it's just RFI. And just so you know, the entire window on the left here is represented by this tiny little box on the right here. That's how much I've zoomed out. So you can actually line up these narrow horizontal yellow bands with what's going on in the right boxes here. So that's how you know where it is. So the bottom line is, here are the results. No aliens. Sorry, spoiler alert. We have yet to detect extraterrestrial intelligence. That is not our own. So, okay. At this point, it's about 40 minutes in. I don't want to go over too much. It's about 10 to 1. I have another project to explain to you. I will go through that as quickly as I can, but feel free to drop off if you need to. I totally understand. I just want to let you know. Hopefully this will take another 10 or 15 minutes, and then we can do questions if you like. But again, you know, if I'm boring you, feel free to drop off if you need to. Okay.
Yeah, thank you. And thanks for letting us know that, Nick. And again, any of our members or guests that would like to leave at any time, please feel free to drop off. Thank you.
Also, I've been told that this is being recorded, right? So
yes.
if if you want to watch the rest of it later, that's also an option for you.
Great. Thanks, Nick. Please continue.
Great, thank you. Okay, so yeah, so let's talk about the last project that I've been working on, and that is SETI at Meerkat. Meerkat is, of course, the telescope array that is pictured on the top right here, and not the fun little mammal pictured on the top left, although they do have the same name. Meerkat is operated by SARAO, the South African Radio Astronomy Observatory, and Breakthrough Listen is trying to get commensal operations going on this telescope. So basically trying to use the telescope for SETI research. So what Meerkat is basically small dish, 64 small dish antennas in the Karoo Radio Quiet Reserve of South Africa. Karoo is the name of it. It's a radio quiet reserve, much like the radio quiet zone in West Virginia for Greenbank. Although I believe Karoo is much bigger. Anyway, the operating bandwidth is L-band and S-band. This says that S-band will be operational later this year, but this is an old slide from earlier this year. S-band is now currently fully functional, definitely working. And so they have L-band and S-band, which is great. And so we're hoping to get that working, or yeah, get some observations in those bands. The advantage of using a telescope array like this is that it has one of the advantages is that it has a very wide field of view. So it's many small dishes spaced widely apart, so you can use a very sophisticated computer programming, computer software called interferometry to basically concatenate all of the signals. If they're all pointed at one source, you can basically combine all the signals with a very complex, sophisticated software technique to simulate the longest baseline, that is the longest separation of any two antennas. So the longest separation here, the baseline, is 8 kilometers. Gee, what is that? Is that 5 miles? Anyway, so you basically are looking, that's basically a telescope of that size. Of course, they're actually small little antennas spaced widely apart, so you lose a lot of resolution, but really not that much. And it's really impressive what you can do with it. And this telescope array will be integrated into the SKA, the Square Kilometer Array, in the later this decade. And that is going to be operational in South Africa and Australia and New Zealand, and hopefully a couple other countries that might sign on. But it's already being built on top of what already exists at Meerkat and the other array in Australia. And it's going to be revolutionary for radio astronomy. It's really impressive, and we're really looking forward to that. But in the meantime, we have Meerkat, which is also doing an amazing radio observations. So traditionally, the way that we observe things, right, is we take our telescope and we point it at a thing, and that's what we observe. We observe that thing. So we look at the sky, and in the field of view, we have a bunch of stars, but we're really only concerned, usually, we're really only concerned about one thing in that field of view. And so what you see is what you get. But the cool thing about Meerkat and interferometry and using multiple telescopes is that sophisticated software technique that I discussed earlier can be used to also do multi-beaming. It can be used to form multiple circles. So basically you have your circle field of view, right? And then you can form smaller fields of view within that circle on different stars. So you don't have to look at just one thing. You can look at multiple things at the same time using software techniques. It's very impressive. And so with a wide field of view and the ability to form multiple beams on multiple objects, you can actually observe many things all at once, and it's awesome. So the idea here is to observe commensally, which is a scientist has control over the telescope. They point it where they want. Say they want to look at a pulsar, or they want to look at a nebula, and we're like, hey, we don't really care about that. There's probably not planets there that we care about. That's not really interesting to us. But that doesn't matter. They take data of whatever science project they're doing, and then Breakthrough Listen also gets a copy of that same data at the same time, and we, the Breakthrough Listen team, can form beams on the other stars that are in the field of view that are interesting to us, right? We can take a look at the other stars that might have planets around them that are in the field of view that the other scientist doesn't really care about, but we do. And so we can observe commensally, or at the same time. So we can basically do 64 beams at the same time. So 64 targets at the same time. So the problem there, of course, is that the scientist has control of the telescope, and they point it where they want to. We don't get a say in that. Breakthrough Listen doesn't get to tell the telescope where to point. They just get a copy of whatever data comes in. So in order to ensure that they can use whatever data comes in, they built up this 26 million star catalog of all the nearest all the nearest stars that are interesting and might have exoplanets of interest. So there's a number of ways that they built this up, but Daniel Check, who's a postdoc at Berkeley Breakthrough Listen, UC Berkeley. Breakthrough Listen operates out of UC Berkeley. He got his doctorate at Cape Town in South Africa, so he's intimately familiar with Meerkat. He built up this. He published the building of this 26 million star catalog with a lot of interesting targets, and noted here is the nearest 1 million because Breakthrough Listen has a mandate to observe 1 million of the nearest stars. So the idea behind the star catalog is it covers the entire sky, so no matter where you point, in theory, you should be able to find some stars in your field of view that are within this catalog and of interest. So it doesn't matter where the other scientist wants to point their telescope, we should be able to find it. Find stars that are interesting, collect the data, and take observations commensally. So Daniel Check also ran the numbers, so to speak, and said, based on the average number of stars in any given pointing, and assuming 80% uptime, how long will it take to reach that 1 million star mark? And it'll take about a year and a half, roughly. But that 80% uptime was sort of pulled out of thin air, right? And they said, I don't know, how long is it, how often is the telescope taking data? Well, let's say 80%. Where did that number come from? Well, that's my job to figure out if that's accurate. So over the summer, over the past year, I parsed the output logs from the Meerkat telescope array. Meerkat's been operating since 2018, so it's doing good science. But Breakthrough Listen is hoping to get commensal operations up and running early this year. So I looked at the output logs that Meerkat's putting out, and I had to sift through it and sort of pick out where all of the completed observations are taking place and filter out like all of the garbage, the warnings and the errors And so that was fun. I built up a data frame, which is basically just a fancy table of all the observations that were completed, when they were conducted, how long did they take, what was the pointings, who was included, et cetera, et cetera. And in this data frame, I basically just collated all of the completed observations, and you can see highlighted in green all of the good science observations, and in the red, you can see things like the LayCal and engineering linearity experiment, which are basically like, tests and not very interesting because they don't produce science data, right? So it's basically like the engineers like testing out the telescope, like pointing it at whatever, sometimes just nothing in particular, just to make sure that the telescope is up and running. So it looks like it's a completed observation, but it's not. So that's not useful to us. We need usable science data. So I had to parse that out. I had to filter that out and figure out, okay, how much of these observations are actual usable science data. And so I analyzed that, and basically the bulk of this is not very important. The bottom line here is circled in orange, and that is that of all of the time, out of all of the time, Meerkat is collecting science data about 68% of the time. Cool, that's great. So as a commensal observer, Breakthrough Listen is supposed to be getting a copy of all of that science data. So I also ran the numbers to see how often is Breakthrough Listen actually getting included. And this is a plot of the results because, as a scientist, plots are fun, and that's the way we like to communicate with things. And so what I've plotted here is for a year from July to June 2020 to 2021, in gray in the background is the number of hours in every day that Meerkat was operational and collecting science data. And the total average of that is the horizontal dashed purple line there. And it's a little over 16 hours out of every 24-hour period. And so then plotted on top of that in green is the BLUs, that is the Breakthrough Listen user supplied equipment. That's the instrumentation a vocabulary for Breakthrough Listen. So Breakthrough Listen is getting what you see in green here. And the average of that is plotted in this dashed horizontal blue line. And you can see those don't match up, which is unfortunate. You would like those to be perfectly aligned, right? You'd like to be Breakthrough Listen to be getting 100% of that data, but that's not quite what's happening. And part of that could just be, I didn't filter out all of the things, maybe. It could just be that they dropped some packets. There's a number of different reasons, but the bottom line is it's not really disputable that Breakthrough Listen is getting a little less than 12 hours out of every 24-hour period of observation. You'll notice, of course, that Breakthrough Listen doesn't actually start getting anything until mid-December. There was a couple of blips there where they were testing the system, but they didn't really turn on until mid-December. Basically, they had to come to an agreement with the other observers to say, yeah, it's cool that Breakthrough Listen is getting a copy of our data. There are ethical and proprietary concerns with doing science, and so everybody had to sort of get on board and flip that switch. So anytime a scientist goes and takes data, they have to make sure that they flip the switch that says, yes, Breakthrough Listen also gets a copy of this data. So that's what happened there. So again, I just ran the numbers, bottom lining it here for you. Breakthrough Listen can expect an actual uptime. The amount of science data that Breakthrough Listen can expect to get from the Meerkat telescope is about 12 hours out of every 24-hour period. Not quite 80%, unfortunate, but not bad. So that's basically the conclusion that I came to. I'm also working with the Breakthrough Listen team to construct the database for the data products that will be coming in as they begin to actually collect the data. It's a very complicated process, but I'm still working with them, and I'm very excited to be working with them, even though I'm basically a volunteer. not really, only loosely affiliated with breakthrough list and not officially. But that's sort of the way science works and the way that, grad students work. Anyway, final remarks here. Thank you all for being patient and sticking with me. I really appreciate it. But I really believe that SETI, commensal SETI observing is the future. The best way, I think, to conduct a SETI research is to do it at the same time as doing other more conventional research. And that really aligns with Frank Drake's vision for SETI research, outlined here in his paper in 1965. And he stated that any project aimed at the detection of intelligent extraterrestrial life should simultaneously conduct more conventional research. I think most notably, he was concerned that scientists who invest all of their time and effort into SETI research might get a little disheartened, burnt out by non-detections. That certainly has been the case for the last 60 years. We have detected nothing. And there's no reason why you can't do multiple disciplines at the same time in astronomy. That's the way that he conducted his very first observations, and that's the way that he thinks that SETI observations should continue forward, and I tend to agree with that. And to that end, one last thing is that, as was noted in my introduction, I came to Penn State to actually study exoplanets. It wasn't until I actually got here that I realized that SETI research was even a thing. Of course, as soon as I realized that, I was like, oh, that sounds really cool. I want to do that. And so I started to work on that. But then, my exoplanet interests sort of took a back seat. But I've made it very clear to my advisor that I do want to do exoplanet research. And he's found some interesting projects, possibilities for me. And so in the near future, I'm actually going to be doing some exoplanet research, hopefully on disintegrating exoplanets, putting together a JWST proposal to study disintegrating terrestrial planet, which would be exciting because it would mean basically, bottom line, we would, for the first time, be able to disentangle the exact chemical elements that make up a rocky exoplanet. But that's for the future, and that's what I hope to work on in addition to SETI. So thank you all for being very patient. I really appreciate it. That's pretty much my presentation. And if you have any questions, I am more than happy to answer them. Thank you.
Thank you very much, Nick. Really appreciate it. If you do have questions for Nick, you'll have to unmute yourself because Rick Lazarick muted you all. So please unmute yourself if you'd like to ask questions.
Yeah, I'd like to ask a question, Nick.
Sure.
This new telescope that is being unveiled is supposed to be used to see, is it up?
I can't quite make it out.
You're generating feedback.
I'll start over. And there's a new telescope that NASA is going to be using to search for. Is that up? Is that working?
Something about a new telescope. I'm getting a lot of echo that's really difficult to understand what you're saying. Maybe David, could you your mic for a minute?
I think, Nick, what he asked is that NASA was working on a new telescope. Is that operational yet?
NASA is working on a number of new telescopes. The one you may be talking about is the JWST. That's going to be launched in less than a week, next Wednesday.
Right.
Right. Okay. Yeah. So JWST is being launched next Wednesday. That is a super tense thing for everybody in the astronomy community. It's not launched yet, but it will, in theory, be able to detect. It will be used for many things, but one of them will be detection and classification of exoplanets. Yes.
Will you be using it?
I hope to. I would love to, but everybody wants to. So getting time on JWST is difficult, and the project that I alluded to right at the end there, disintegrating exoplanets, the JWST proposal. So cycle 1 proposals have already gone out and been decided. It's already decided who's doing what science on JWST for the first year and a half, maybe. I forget the term, the length of the cycle. So that's already been decided. So the proposal that had already been put in for cycle 1 and rejected, but just barely apparently. And so my advisor thinks that I can contribute by basically shoring up that proposal and resubmitting for cycle 2. And it's almost guaranteed that we'll get it for cycle 2, which won't be submitted till next December. But it still will be very competitive. And so, it's hard to say.
Hey, Nick, this is Dave. I have a quick question. How much of this research that's being done is being funded by the government and therefore is classified? And likely you wouldn't even know what's happening in this research.
Great question. Most research is funded. Most research is funded by NASA and the NSF. That most science is funded by NASA and the NSF. That's public funds, and it is not. There's no caveat for secrecy or classified information. People who conduct research with military money, however, that is classified, and I would have no idea about that. Yeah, let's go with that. The big player in the game, as I mentioned, is Breakthrough Listen. They're funded privately, and they aren't necessarily obligated by the same rules that NASA and the NSF play by to publish. But as far as I know, we know everything that there is to know. For the most part, military is concerned with other things. There are certain things that I have worked on in the past where the military has expressed interest, particularly in adaptive optics and imaging. And so there could be projects you might, yeah, I mean, there's always boogeyman stories, but I can't comment on things that I can't comment on. Like I just don't know. But for the most part, most science that we know of is funded by NASA and NSF, and there's no classification, anything with that. So, in fact, it's written into their mandates that we publish in a certain timeline.
So NSF is the National Science Foundation, just as a reminder.
Yeah, and that's actually who's funding me. I'm funded personally by the National Science Foundation, GRFP, the Graduate Research Fellowship Program. Basically, they're the people paying for my graduate education, which is very, very nice.
Yes, thank you, Uncle Sam.
Yes.
So, does anybody else have
a question? Hopefully, kind of a non-answer.
The one area that we didn't get to talk about, and we hope to have you back for, is your discussions on exobiology or astrobiology. So if everyone is amenable to it, we would love to have you back and have you give us a presentation on that in the future.
Sure. Yeah, I would love to. Astrobiology is interesting and difficult. It's interdisciplinary and combines biology, geochemistry, and astronomy. And I know astronomy, so yeah, 2/3 of what I learned in astrobiology go right over my head.
Gotcha.
But yeah, no, I can definitely do my best if you want to have me back.
It looks like Glenn has a question.
Oh, yeah. What do you think about the Fermi paradox? It's a great question. So the Fermi paradox is actually a misnomer. The Fermi paradox was famously So the Fermi paradox is actually a conversation that Enrico Fermi had over lunch before SETI even began. He basically just like made an offhand comment, and as a famous astronomer, of course, people were listening in and just took it and ran with it. But he basically made an offhand comment saying, if they're out there, where are they? And basically he was saying like, why hasn't anybody contacted us yet? And why don't we see anything yet? But it's been sort of blown out of proportion at this point, and built into this thing called the Fermi paradox that is that basically astronomers use to assert that there's the great silence, that if there were civilizations out there, we should have heard them by now. So so why don't we hear anything? Why don't we see anything? And basically, I think that it is not really a paradox at all. I think it's not really interesting in that we really just haven't looked hard enough. As I showed you earlier, the electromagnetic spectrum is huge. Even just the radio alone is super wide. And finding those little narrow signals, remember how I showed you the blow up of that one little thing turned into that tiny little bar, and that was still so minuscule of the entire spectrum. It's impossible to comb it all. And that was just one pointing. Like that was just looking at a very tiny little dot in the sky. So it's just crazy to think that we've seen that we've searched the sky. We haven't. We just basically have not searched enough to really make any claims about anything at all. A recent paper was just published by my PI to update the very famous Jill Tarter quote that says, Jill Tarter basically, he was a very prominent scientist, the inspiration for the movie Contact. She very famously said something to the effect of, if we're looking for, if SETI is like looking for fish in the ocean, what we've done is taken a glass of water, scooped up the ocean, and said, hey, there's no fish in there. That's ridiculous. We have not searched the ocean, right? We have not searched enough of space to definitively claim that. And my PI recently published a paper where they updated the statistic based on all of the projects published and done, and they said, it's not a glass of water, more like a bathtub. So fill up a bathtub with ocean water, and if there's any fish in there, then you've detected something. And if there's not, then there's definitely no fish in the ocean. That's not really a great claim. So that's what I think of the Fermi paradox is. We just don't know enough yet. Got to do more research, fund more research, pay more taxes, please.
Yes, keep Nicholas in school. Yes.
Yes.
Which is great. If no one else has any more questions, I want to thank Nicholas for taking the time out of his schedule. I think he's just concluded his last semester, within the last 10 days. So preparing this for us is a chore, and I really appreciate it very much. Thank you. We will send you the link to when we post to our YouTube page. The Rotary Club of Trenton has a YouTube page, and you all should be liking it and subscribe to it. So please do that. I'm told that whenever I talk about social media, I have to tell you all to do that. That and our Facebook page and our Instagram and our LinkedIn and TikTok and whatever other stuff there is out there. So I want to thank you all for being able to stay long and listen to the next presentation. I once again want to wish everyone a Merry Christmas and Happy New Year. There's Christy. Chris has got her